Part 2. Question 21. Which statement concerning solutions is false? A solution forms when the solvent and the solute react to form a new substance. I see a problem right away. When we're making a solution, we're not having any kind of reaction. So A is false. If you take a look at the other four, a solution has its components uniformly distributed throughout the mixture. This is true. A solution is likely to form when a solute and a solvent have similar polarities, right? You might remember like dissolves like, so that's true. A solution is a homogeneous mixture of two or more pure substances. Absolutely, this is true. Homogeneous mixture is a solution. And the last one, a solution is composed of a solvent and one or more solutes, of course. So the answer is A. (22) It says if I have 5.20 grams of HCl and I add it to enough distilled water to form 3 liters of a solution, what is the molarity of the solution? So you might remember the formula for molarity, and that molarity is the number of moles divided by the volume in liters. I'm given the mass of HCl, but all I have to do is go to the periodic table to determine the molecular weight of HCl. So for the number of moles of HCl, I'm going to plug in my 5.20 grams, and I'm going to divide that by the molar mass of HCl, which is 36.46 grams per mole. And then, of course, I'm going to divide that by my volume, which is 3.00 liters. So you can see that my mass units are going to cancel out, so I should end up with moles in my numerator, and I still have my volume in my denominator, and when you punch that in your calculator, you get 0.0475 molar, or moles per liter. So the answer is A. In 23, it says enough water is added to 50 milliliters of a 0.660 molar sodium hydroxide solution in order to bring the total volume to 450 milliliters. What is the total molarity of the diluted solution? So this is a problem that deals with dilution. So the formula we're going to use is M1 times V1 is equal to M2 times V2. We already are given the initial volume and the initial molarity, and we're given the final volume as well. So that means we need to solve for the molarity, right? Because it's asking us for the molarity of the diluted solution. So we'll say M2, and rearrange our formula, is going to equal to M1 times V1 divided by V2. So we just plug in our numbers, 660 molar multiplied by the initial volume, which is 50.0 milliliters, and then we divide that by 450 milliliters. You can see that my units of volume cancel out. I end up with a concentration, which is going to be 0.0733 molar. And that makes sense because we're taking this solution, right, or we're taking that stock solution, if you will, and we're diluting it, right, because we're adding more solvent to it. So the molarity should be lower. The concentration should be lower. Number 24, a student mixes 4 grams of potassium nitrate with 5 ml of water at room temperature and observes that most, but not all, of the potassium nitrate has dissolved. Which statement concerning this solution is true? So in order to get additional potassium nitrate to dissolve, the student can add more solute. Well, the solute is potassium nitrate. So if I add more, it's not going to go into solution. What about B? It says the solubility of the potassium nitrate in water has been exceeded. Yeah, that seems reasonable to me because the person or the student can't get any more potassium nitrate to go into solution. So the answer is B. If we take a look at the other choices, so C, the solution is considered unsaturated. Well, that's not true. It's definitely saturated because most, but not all, of the potassium nitrate has dissolved. Potassium nitrate is a water-insoluble ionic compound. Well, that's not true. It's an ionic compound. That's true, but it's definitely soluble. And then E, the solution is considered supersaturated. It is definitely not a supersaturated solution because that's when you heat up a saturated solution and then you cool it down slowly. So that doesn't apply in this case. Number 25 says that 1 mole of sodium chloride is added to 100 milliliters of water in beaker A, and 1 mole of glucose is added to 100 milliliters of water in beaker B. How much more will the freezing point of water be lowered in beaker A than in beaker B? So this deals with freezing point. So freezing point depression, right? Because we're adding particles to water, and that's going to depress the freezing point of the water. And the formula that we use for that is that delta TF, so the change in the freezing point, is going to be equal to I times the proportionality constant, Kf, times the molality. But what we're concerned with here is I, because I is the number of particles. So therefore, you can see that I and the change in the freezing point are going to be directly proportional to each other. So that means whichever one of these has more particles, sodium chloride or glucose, is going to depress the boiling point more. So if I take a look at sodium chloride, NaCl solid, if I put that in water, I'm going to end up with a sodium ion and a chloride ion because it's an ionic compound. So I end up with 2 particles. If I try the same thing with glucose, C6H12O6, glucose is a covalent compound. So when I put that in water, it's just going to dissolve in the water. And it's not going to ionize because it's completely made of nonmetals. So I'm just going to end up with this. So there's only 1 particle. So again, the freezing point is going to be lowered more when I have more particles. So you can see that I have twice as many particles with sodium chloride than I do with glucose. So therefore, if the I is equal to 2, then the freezing point should be lowered by twice as much. So the answer will be C. Number 26, which of the following correctly describes what happens when red blood cells are placed in a hypertonic solution? So if I think about a hypertonic solution, so if I have some kind of vessel like this, okay, and let's say it's got some water in it or something, right? But it's a hypertonic solution, so that means it's got, a lot of particles, right? And then I have my red blood cell in the middle, okay? So here's my red blood cell. What's going to happen is that the water that's in the red blood cell is going to leave that red blood cell and it's going to go into the hypertonic solution like this. So ultimately what's going to happen is it's going to force that red blood cell to shrink. So it says here in B, there's going to be a net movement of water out of the red blood cells, causing the red blood cells to shrink and collapse. And we have a fancy name for that, which is crenation. Number 27, the solubility of a solute is best described as which of the following? So A says the mass of solute necessary to dissolve in 1 liter of water. B says the maximum amount of solute that can be dissolved in a specified amount of solvent. That already sounds right to me. It's the maximum amount of solute that you can put into a specific amount of solvent. Number 28, sodium phosphate dissolves in water to produce an electrolytic solution. What is the osmolarity of a 2.0 times 10 to the negative 3 molar sodium phosphate solution? Osmolarity is equal to I times the molarity. And I is related to the number of particles, our Van Hoff factor. So how many particles are there in sodium phosphate? So when I take my sodium phosphate, okay, and it is in solution, I'm going to end up with 3 sodium ions and 1 phosphate ion. So how many total ions do I have? I have a total of 4 ions or 4 particles. So my osmolarity is going to be equal to 4 multiplied by my concentration, which is 2.0 times 10 to the negative 3 molar. So it equals 8 times 10 to the negative 3 osmolar. Question 29, how many moles of potassium chloride are present in 50 milliliters of a 0.552 molar solution? The units for molar are moles per liter. So I have volume here and I have volume down here. So all I have to do is multiply these two and I can end up with the number of moles. So if I want the number of moles of KCl, I'm going to take my concentration, which is 0.552 moles per liter, and I'm going to multiply that by the volume of the potassium chloride solution in liters. I've already gone ahead and converted that into liters, so you just divide it by 1,000 and you get 0.0500 liters. So we'll plug that in, 0.0500 liters, kind of running out of space here. So you can see that the units for volume cancel out, and I end up with the number of moles of potassium chloride being equal to 0.0276 moles. The next question, which diagram best represents the composition of an aqueous calcium chloride solution? Well, what's happening when I have aqueous calcium chloride? So I take my calcium chloride, if it's solid, and I put it in water, and I end up with calcium 2 plus ions, plus I'd end up with 2 chloride ions. So what does that tell us? I have two times the amount of chloride ions. Now if the chloride ions are these darker spheres, you can see that in B, I have 2 times the amount of chloride spheres, or of those dark spheres that represent the chloride. So I have 4 of those, whereas I only have 2 of the calciums. So B makes the most sense. Number 31, what term best describes a solution that is in equilibrium with undissolved solute? This is a saturated solution. Number 32 says, increasing the pressure of a gas over a solution increases the solubility of the gas in the solution. This is an example of which law? The law is Henry's law. And Henry's law states that the number of moles of a gas dissolved in a liquid at a given temperature is proportional to the partial pressure of the gas above the liquid. So it's a good idea to have Henry's law memorized. Number 33, calculate the mass in grams of sodium chloride that is present in a 500 milliliter solution that is 0.900% mass over volume. So for that, if we're solving for the mass in grams, we're going to need the formula of percent mass over volume, which is percent mass over volume is equal to the mass of my solute in grams divided by the volume of the solution in milliliters multiplied by 100%. So we're solving for the mass of sodium chloride in grams. So let's plug in our numbers. So the percent mass over volume is 0.900. I'll put in X for my mass. My volume is 500.0 milliliters. And then, of course, I'm multiplying by 100%. So I can rearrange that formula to solve for X. So X is going to be equal to 0.900 divided by 100. And then I'm going to multiply that by 500.0. So when I solve that, I get that X is equal to 4.50, and the units will be grams. Question 34, if the concentration of magnesium 2 plus in solution, so that's the magnesium ion, if the concentration is 3.0 times 10 to the negative 3 molar, what's its concentration expressed in milliequivalents per liter? So you might remember the formula, which is the number of equivalents per liter is equal to the number of equivalents, which is our charge, the number of units of charge, divided by the number of moles of a particular ion. And then I'm going to multiply that by the number of moles per liter. So the moles of that ion per liter. So you can see that the moles of ion are going to cancel out, and I'll end up with equivalents per liter. Now, of course, we're asked for milliequivalents, and we know that there's 1,000 milliequivalents for every equivalent. Anyhow, so let's get started here. So if we want to solve for the number of equivalents per liter to start off with, well, magnesium has a 2 plus charge, so that means there's 2 units of charge. So we'll plug that in. So we have 2 equivalents for 1 mole 1 mole of Mg2 plus ions. And then we know that for every 3.0 times 10 to the negative 3 moles of the Mg2 plus ion, we have 1 liter. So look, my units cancel out like that, and I end up with the number of equivalents per liter. So if you're thinking all I have to do is multiply the concentration by the number of units of charge, the answer is yes. So I end up with 0.0060 equivalents per liter. Now I'm going to convert that into milliequivalents. So if I have my 0.0060 equivalents per liter, and I know that in 1 equivalent I have 1,000 milliequivalents, that's going to cancel, and I'm going to end up with 6.0 milliequivalents per liter, which is C. Question 35 asks us which statement concerning solutions is false. So aqueous solutions have water as the solvent. That's definitely true. Solutions are homogeneous mixtures. Yes, so you should know the difference between a homogeneous and a heterogeneous mixture. C, solutions consist of solutes and solvents. That's true. A solute is dissolved in a solvent. The solute is present in a lesser amount. The solvent is present in a larger amount. D, solutes cannot be filtered from a solution. Well, that's true because they are completely dissolved. And then E, solutions are always liquids. That's not necessarily true. A solution could be a mixture of gases, or it could be a mixture of solids. For example, the air that we breathe is a solution. It's a solution of nitrogen, oxygen, and several other gases. Number 36, an unknown amount of water is added to 75 milliliters of a 3.5 molar sodium chloride solution. What can be said for certain about the concentration of the solution that results? Well, if we're adding water to a solution, what's going to happen is that the molarity should decrease, right? Because we're diluting it. So this is dilution. And the reason that the molarity, right, so dilution, so the molarity is going to decrease. And the reason why is because if you think about, if I have my container that's 75 milliliters and I have a certain number of particles in that volume, well, if I increase the volume, so let's say I increase the volume by diluting it, so this is my new container. Let's say I have 1, 2, 3, 4, 5, 6, 7, 8, whatever. Now 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, 8. So if I have my 8 particles, now I have the same number of particles, but I have a lower molarity, right? The molarity has decreased because I have the same number of particles, but dividing by a larger volume. So if my denominator increases, but my numerator remains the same, my concentration is going to drop. So it says here, the concentration of the resulting solution will be less than 3.5 molar. Number 37, a chemist needs 0.725 moles of acetic acid for a particular reaction. What volume of a 1.50 molar acetic acid solution is necessary to provide this amount? Well, we know that concentration, the 1.50 molar, is equal to 1.50 moles per liter. I'm looking for a volume, but I already know the number of moles and I know the concentration. Well, hopefully you can see that in order to determine the volume of my acetic acid, if I take the number of moles, which is 0.725 moles, and I divide that by the concentration, which is 1.50 moles per liter, my moles end up canceling out, and I end up with my volume. And that volume is 0.483 liters of acetic acid. Number 38 asks us, what is the boiling point of a 0.5 molal solution of sodium chloride? And we're given our proportionality constant for delta TB of 0.52 degrees Celsius per molal. So you might remember that small m is molality, which is different from molarity. So molarity is moles per liter, and molality is moles per kilogram of solvent. So you also might remember that delta TB So the change in boiling point is going to be equal to I, the Van't Hoff factor, multiplied by the proportionality constant, multiplied by the molality. Well, if we have sodium chloride, we know that our Van't Hoff factor should be 2, because sodium chloride, when I take sodium chloride and I put that in water, I end up with 2 particles. I end up with the sodium cation, and I end up with the chloride anion. So I have I is equal to 2. So if I plug all this into my equation, I have 2 times the proportionality constant, which is 0.52 degrees Celsius per molal. And I have my molality, which is 0.5 molal. So you can see the molality cancels out. So I have 2 times 0.52 times a half, and I end up with a delta TB being equal to 0.52 degrees Celsius. So what's the boiling point of water? The boiling point of water is 100 degrees Celsius. And you might remember from colligative properties that we talk about freezing point depression and boiling point elevation. So that means the boiling point of water is going to be elevated by the 0.052 degrees Celsius. So the boiling point of my water, so the boiling point, I'll just write it down here, is going to be equal to 100.00 degrees Celsius plus 0.52 degrees Celsius. So my boiling point is going to be equal to 100.52 degrees Celsius. So my boiling point, again, is elevated to A, 100.52 degrees Celsius. Number 39, a patient requires 100 grams of glucose in the next 12 hours. What volume of a 5.0% mass over volume glucose solution should be administered? I'm kind of running out of space, so I'm just going to solve number 39 down here just for the interest of space. So let me move that up a little bit. There we go. So let's get started. So the first thing you need is the formula for percent mass over volume is equal to the mass of solute in grams divided by the volume of the solvent in milliliters, and then I multiply by 100%. I'm given the percent mass over volume, which is 5.0. I'm given the mass, which is 100 grams. And I'm looking for the volume, so I'll solve for x. So multiplied by 100. So when I rearrange this formula, I'm going to get that 100 over x is going to be equal to 0.05, and I got there by just dividing both sides by 100. So then if I rearrange this again, I get x is going to be equal to 100 divided by 0.050, which is going to be equal to 2,000 milliliters. I didn't express it with the proper number of sig figs, but you get the idea. And then I'm going to convert 2,000 milliliters into liters. I know that there's 1,000 milliliters in 1 liter. So I end up with a volume of 2.0 liters. And if you're wondering why only 2 sig figs, it's because there's only 2 sig figs in the percent mass over volume. So that's why I have 2 sig figs. So the answer is 2.0 liters. So with that in mind, let's take a look at the very last question, which is just a true and false question. There are no true and false questions on the actual exam. An alloy such as brass is an example of a solution in the solid state. The answer is yes. Brass is actually a solution. It's actually made from zinc and copper. So that's what an alloy is. It's a mixture of metals. And a solution can be a homogeneous mixture of... a solution can be in the liquid state, and it can be in the gas state, and it can also be in the solid state.